In this video, we're going to go through the Unit 4 practice test. You may notice it's a little bit of a different video format. All right, I have a new thing that I'm going to try out, so just let me know if you like this video format or not. So one thing, instead of going through like the individual pages, I just put them on slides so we can just look at one problem at a time. All right, our first skill is finding the integral of a function geometrically. So we just have to remember that this notation over here, this little kind of curly s, means area. All right, so it's telling us to find the area from -6, so that's here, up to 3, which is right there. So the one thing you don't want to do with these problems is find more area than you have to, so just make sure you're finding only the area required. And then I just want to break it up into some easily found pieces. So right at the start, I kind of have this triangle that I can find. And then after that, I kind of have another triangle here. I have a rectangle here, and a big triangle all the way to the end. All right, so breaking up these into kind of individual shapes is going to help you find this. So this triangle here is 1 wide and 1, 2, 3, 4, 5 high. So the length times the width is 5, and we divide that by 2. So this triangle has an area of 5/2. This one is 1, 2, 3, 4, 5 high and 1 wide, so this one's also 5/2. All right, this rectangle is 2 wide and 5 high, so this rectangle has an area of 10. And this triangle, 5 wide, 1, 2, 3, 4, 5 wide. All right, so that's 25 divided by 2 is 25/2. All right, now I just want to add these all together, and just remember one extra thing is that when I'm doing these area problems, any area underneath the x-axis is negative. So I'm going to have my positive 5/2, my first triangle, and I'm going to subtract the next triangle, which is 5/2. I'm going to subtract the 10, because that's on the bottom, and subtract my 25/2. And right away, these 5/2 cancel out, and I just get -10 minus 25/2. And technically, I'd be fine with that. If I want to, I can say this is -20/2 minus 25/2, and that's -45/2. Right? Or you can write it as decimal. That's basically the idea of this. This symbol means area, and just find the area between those x values that we're being asked for. So the next problem is the same graph, but my integral is different. So now it's asking me to find from -5 to 9. So -5 is here, and then 9 is there. All right, so I'm trying to find the areas between those two places. Well, I already found some of these areas. So this triangle here, actually I just draw the triangle. That triangle there was 5/2. This rectangle was 10. This triangle was 25/2. So some of the work I did for the last problem is going to help me here again. I just have a couple extra things to do because last time I finished at 3, this time I finished at 9. So here I have another triangle. This is, and let's see, that's 3 wide, 1, 2, 3, 4, 5 high, so that's 15/2. And this one is, this rectangle here is 3 wide, 1, 2, 3, 4, 5 high, so that's a total of 15. Right, just make sure you don't have to divide the rectangles by 2 because they're rectangles, not triangles. All right, now I can put together again everything for the final answer, and just remembering that the things below the x-axis are negative, so -5/2, -10, minus 25/2. Now everything above the x-axis is positive, plus 15/2, plus 15. And combining things, you see this is -30 plus 15 gives me -30/2. The -10 and the plus 15 give me plus 5. And just getting a common denominator, I can combine everything. And I get -10 for my final answer. All right, but again, break it down into shapes. Generally, triangles and rectangles are the easiest ones. Find the areas of each of those shapes, and then just add them together, remembering anything below the x-axis is negative. All right, next problem. We're finding area from -5 to 7. So again, always just make sure you're only finding the area you need. So -5 starts there, and 7 is there. All right, so I'm finding this whole positive area. I want to break it up into smaller pieces. So I have my triangle I could do there. I have this kind of rectangle at the end, and I have this kind of curved bit here. All right, how can I find the area of this curved bit? Well, I can find the area of the full rectangle that I just kind of made, and then get rid of the semicircle. All right, so those are the three shapes I'm going to have. I'm going to have a triangle, a rectangle, and a rectangle subtracting a semicircle. So the straightforward ones are the ones we've already done. The triangle here is 3 wide, 6 high, so that's 18 divided by 2, that's 9. This rectangle is 1 wide and 6 high, so that's an area of 6. And then this rectangle here is, let's see, 8 wide, 6 high, 8 times 6 is 48. And I have to subtract off the area of this semicircle. All right, so the area of the semicircle is pi r squared. All right, what's the radius? Well, it's 8 all the way across, which means the radius is 4. All right, so it's going to be pi times 4 squared. That'd be the area of the full circle if it continued up here as well, but we just want the half of the circle. All right, so we can just simplify a little bit. See, this 16 over 2 is 8 pi. And in this problem, everything is positive, so I'm going to get 9 plus 6 plus 48 minus 8 pi. And I can combine the numbers, the like terms. So let's see, 48 plus 16 is 54. That's going to be 65 minus 8 pi. So adding up the numbers together and then still minusing that 8 pi. All right, so that's how you find the area if we know the shapes that are given. All right, our next skill is approximating areas using Riemann sums. This is one of those things that we've learned new ways to find areas exactly, but we always have to go back and remember kind of the basic blocks that we had as well. So Riemann sums, just remember the basic idea is you have your graph, and then we're going to use a bunch of rectangles to approximate the area. All right, so here we're trying to find the area from 4 to 12, and we're breaking up into 4 subintervals. So let's look at what that's going to look like on the number line. All right, so we're starting at 4. We're ending at 12. I'm going to break it up into 4 equal pieces. All right, so how wide is each of these pieces going to be? Well, 12 minus 4 is 8, so we're trying to cover a distance of 8. Break them into 4 pieces, so each thing is 2 wide. So it'd be 4, 6, 8, 10, 12. All right, I like making this number line because it's helpful when I do the next step. So now I have 4 different rectangles that are going to be made, and I'm doing a trapezoidal Riemann sum. So actually not making rectangles, I'm making trapezoids. All right. And how do I find a trapezoid Riemann sum? Well, for each interval, I'm going to have kind of 2 different heights on my interval, and then the area of a trapezoid is the height, or I guess this guy's the base, times the average of the heights. All right, so I'm just going to have to do this for every single one of my intervals. So I'm going to do this 4 times. So let's see. The first trapezoid has a width of 2. The height on the left-hand side is when I plug 4 into my function. So if I plug 4 into my function, I'm going to get 21. The right-hand side is when I plug 6 into my function. That's 30 plus 1 is 31, all over 2. All right, and we'll simplify at the end. I just want to show the steps. All right, next trapezoid has a width of 2. The left-hand height we already know is 31 because that's when I plug 6 in. And the right-hand height is going to be 41 because that's when we plug 8 in. All right, so that's my next trapezoid. My third trapezoid, width of 2, that's not going to change. Left height is 41. Right height is when I plug 10 in, that's going to be 51. I'm just averaging those. And the fourth trapezoid, width of 2. On the left, I plug in 10. On the right, I plug in 12. And now it's just a bunch of simplifying this trapezoid. The average of 21 and 31. Is 52, and then divide that by 2 is 26. Which means this pattern is probably going to continue. 31 and 41, the average is 36. The average here is 46. Average here is 56. And then I'm multiplying all these numbers by 2. So this is 52. This is 36 times 2. 72. This is going to be 92. This is going to be 112. All right, so this is the tedious part of Riemann sums, is finding all of these things. And now my final answer, my approximation, is adding all these together. So my approximation for this integral, let's see, so we have 52 plus 72 plus 92 plus 112. And that gives me 328. All right, so that's my approximation for the area that I'm trying to find. All right, so this one's a trapezoid one. This one is the most tedious because you have to do these extra steps of averaging out the two sides. All right, but it's only 4 subintervals, so you just have to do these averages 4 times, get all your answers, and add them together. All right, next one. A little bit more complicated function, but now we're just doing 3 subintervals. All right, so again, I like to start with these number lines to kind of visualize what my intervals are going to be. So my number line here, I start at -2, and I finish at 4. All right, how wide is each subinterval going to be? I'm covering a distance of 6. All right, -2 to 4 is 6. And I'm breaking up into 3 subintervals. So just like last example, our intervals have a width of 2. So my next interval would be 0, and then 2, and then 4. Right. Here I'm just doing 3 subintervals. So my first, and I'm doing a left Riemann sum, so not a trapezoidal sum, which means they are rectangles. So each of my rectangles, my first rectangle, the width is going to be 2. And I'm doing a left Riemann sum. So for this first rectangle, I'm going to plug in -2 into my function. So let's see what g of -2 is. It's -2 squared plus 3 times -2. Positive 4 minus 6 is -2. All right, so the height there is -2. My second rectangle, again, width of 2. In this second interval, I'm plugging the left value because I'm doing a left Riemann sum. I plug in 0. That one I can do in my head. That one's 0. And my last Riemann sum, width of 2. Height is when I plug 2 into my function. So let's see what that is. 2 squared plus 3 times 2, which is 4 plus 6, which is 10. All right, so that is going to be my next height. So each of these, if I multiply them out, I get my values, and then my final estimation for my area is when I add those together and I get 16. So very similar to the last one. Again, the Riemann sums I know are tedious because you're doing this like repetitive process, but it's really important that you know how wide your intervals are and you know which value you're plugging in. So if we're doing a right hand sum, this would all be the same except for that I'd be plugging in 0 first, then 2, then 4. If I was doing a midpoint one, then I'd have to plug in -1, 1, and 3. All right, those are the only rectangle ones that we have to deal with. If it was a trapezoid one, we do it just like the previous problem. All right, so we're going to stick with Riemann sums for our next skill, but now we're using tables. So the only thing with tables is they can be kind of different widths, so you have to make sure you're careful with reading your table. They're not always going to be the same width. So in this one, we're using this table and we're doing a right Riemann sum to approximate 1 to 16. So 1 to 16 is the entire table. All right. And basically each pair in the table is an interval. So I have a 1 to 4. All right, my first rectangle has a width of 3. And then the height, I'm using the right-hand value. And again, the height is when you plug your right-hand value into my function. So my height is 16. So my first rectangle has a width of 3 and a height of 16. My second rectangle is now my next interval from 4 to 8. So 4 to 8 is a width of 4. And again, I'm plugging in the right value every single time. So I'm plugging 8 into my function and I get out 7. Third rectangle, you can see the pattern. I'm going from 8 to 10, width of 2. And again, you can see these widths are different, not like the previous 2 examples. Plug in 10, I get 6. Fourth rectangle, 10 to 12 is a width of 2. Plug in the right-hand side, 12, that's 1. And my last rectangle is 12 to 16 is a width of 4. Plugging in 16, I get 17. So I'm just going to run through the calculator, do all these multiplications. 3 times 16 is 48. 4 times 7, probably could have done it in my head, but 2 times 6 is 12. 2 times 1 is 2. 4 times 17 is 68. And you just have all these different rectangles, and you're going to add these areas together to approximate my area. So let's see, 48 plus 28 plus 12 plus 2 plus 68. My final answer is 158. Right. So only difference really between this and the previous problem is these widths can be different depending on how wide it is in your thing. Just remember you're getting the widths from how far the x values is, but when you plug it in, you're getting a y value out. So those heights of my rectangles are coming from that bottom row. right, next problem, very similar. We're doing from 2 to 10. So again, just like the graphs we're looking at, make sure you're not doing more work than you had to. I'm only doing from 2 to 10. So I don't actually care about this very last part at all. And I'm doing a trapezoidal sum. So I'm going to have three different trapezoids. All right, so my first trapezoid has a width of 2 to 6. My x value width is 4. And remember, with the trapezoid sums, you average out the sides. So on the left-hand side, my height is 5. The right-hand side, my height is 17. And I divide that by 2. My next trapezoid is from 6 to 9. That's a width of 3. The left-hand side is 17. The right-hand side is 23 over 2. And my last trapezoid, 9 to 10, is just the width of 1. And the left side and the right side over 2. So again, just a little bit of a help from the calculator just to save a little bit of time. 5 plus 17 divided by 2 is 11. So this is 4 times 11. This is 3 times 17 plus 23 divided by 2 is 20. And this is 1 times 23 plus 27 divided by 2 is 25. So first trapezoid has an area of 44. Next trapezoid has an area of 60. Last trapezoid has an area of 25. And my final estimation for this area is adding all those together. 129. All right, so these table ones, really no different than the other Riemann sums. You just have to pull the values from the table, and again, the widths can be different. All right, our next skill is using the first part of the fundamental theorem of calculus, which is about accumulation functions. So this first question is about kind of what is an accumulation function, what do they mean? All right, so we have g of x, which is accumulating from 2 to x of this f of t. All right, and f of t is the graph that's shown over here. All right, so just make sure we're careful with that. Now we want to answer these questions about g of x. Well, g of 4, whenever I plug in a number into my function, I replace the x with that number. So it's the same as the area from 2 to 4 of f of t dt. And just like our very first scale, I just have to find the area from 2 to 4. Let's actually just put that little area on the graph. 2 to 4, find the area of this. What's a 2 by 2 rectangle? And that answer is just 4. All right, the next question, very similar. Integral from 2 to 7. All right, again, I'm just replacing that x up there with 7. And it just finds the area from 2 to 7. So I just have to tack on some extra stuff at the end of this, all the way to 7. All right, but this is still just a big rectangle, which is 2 by 5. So the answer is 10. Now the last question, a little bit harder, requires some knowledge from past units and knowledge about the fundamental theorem of calculus. When is g of x increasing? Well, in general, when we're talking about a function being increasing and we don't have that function given to us, like a graph of that function, what we need to do is the function is increasing when its derivative is positive. So we need to figure out when the derivative is positive. So what's the derivative of g of x going to be? This is actually the fundamental theorem, part 1, g prime of x. So basically just take this x and plug it into f is f of x. All right, so the derivative of this accumulation function is just the graph we're looking at. And we want to know when that's positive. So my answer is when it's positive from -9 to -8, right here. And then it's positive from -2 and to the very end at 9. And I'm not really picky about the curved square bracket. I put a square bracket next to -9 because it's a solid dot, versus the other places it's 0, not positive. I'm not really too picky about that for right now, as long as you're recognizing that the derivative is the graph, and we're talking about the graph being positive for those x values. All right, next is just a straight application of kind of what we had to do in that part C. Is if I just want to find the derivative of this accumulation function, again, just take that x, plug it in. The answer is very simply just the square root of x. All right, nothing else to do. Fundamental theorem of calculus, when you know it, the application is really simple. You just plug in a letter into a function. All right, part 3, a little bit more complicated. The first step's still going to be the same. If I'm trying to find the derivative of an accumulation function, I just take this and plug it in. It's going to be x squared plus 3x squared. So I just take the thing that's up here and plug it into both. right? And the only difference is that's the first step. And the second step, now I need to take the derivative. This is the chain rule because this whole x squared is in here. I need to multiply by the derivative of that, which is a 2x. So if I, again, on the test, I would accept that. But generally in a multiple choice question or something, you would see x to the 4th plus 3x squared all times 2x. So if I just kind of simplify that expression, and chances are if this was actually a multiple choice question on the AP exam, you'd see it as 2x to the 5th plus 6x cubed. They try to fully simplify their answers for the multiple choice questions, just kind of force you to do a little bit more algebra. The important thing is you're recognizing the fundamental theorem, you plug this x squared in for your t's, but since it's a chain rule problem, you have a little bit more work to do. All right, and the last one is the most difficult problem you could possibly have for the fundamental theorem of calculus part 1. That's when there's not a number at the bottom. The fundamental theorem of calculus only works when there's a number at the bottom. So how do we make that work? So if we want to figure out we're doing from x to 2x, we need to start at a number. So let's just say like 0 was over here. We can make them both start at 0. And how would these combine to give me the one I want? If I do from 0 all the way to 2x, so I do the integral from 0 to 2x, that's this whole red section. And then I do the 0 to x, that's this green section. If I subtract away the green from the red, then I'm going to get the part I actually want. So I can start these both at 0, but just using some kind of creative integral rules, I can make them so they both actually start at 0. So this function, again, this is not the answer, g of x, the original function is the same as 0 to 2x of t squared dt minus the integral from 0 to x of t squared dt. All right, so I haven't done the derivative yet. I've just rewritten it so that both of these integrals start at a number. And now I can take the derivative, g prime of x. This first derivative is similar to the last example. I plug 2x into t squared. But because it's not just an x here, I have to do the chain rule. I have to multiply by the derivative of 2x, which is just 2. All right, and I subtract. This derivative is much simpler because it's just an x. I just put the x in and get x squared. This one, I can do a little bit of simplifying. 2x squared is 4x squared. Multiplied by another 2 is 8x squared. And these happen to be like terms, and I get a final answer of 7x squared. All right, so this, like I said, this is kind of the most difficult thing you possibly have to do with the fundamental theorem is break it up first and then apply the fundamental theorem. All right, so you can kind of see the 3 stages. Either just plug it in like the first example, plug it into the chain rule like the second example, or the third example, rewrite it, and then do those things twice. All right, for skill 4E, we're using the fundamental theorem of calculus part 2 to evaluate a definite integral. So the fundamental theorem of calculus part 2 says if I want to find the integral from a to b of f of x dx, all right, so if I want to find this exact area, what I do is I use an antiderivative. So I go reverse the derivative process, and then I evaluate it at a and b, which just means I plug in b, and I subtract, and I plug in a. All right, so in actual practice for this problem, I need anti-differentiate 4x minus 2, so I need to remember my reverse power rule. So for 4x, I'm going to add 1 to the exponent, so x to the first becomes x squared, and divide by the new exponent. All right, so that's the reverse power rule. All right, 2 is technically x to the 0, so I'm going to add 1 to the exponent. 0 plus 1 is 1. Divide by the new exponent. And I want to evaluate that at 2 and 5. Before I start plugging things in, it makes sense to simplify. All right, simplify before you plug in things. It'll just save you time. So this is going to be 2x squared minus 2x. All right, at this stage, when you're first doing this, it's always a good idea to make sure, is this actually the antiderivative of what I started with? If I take the derivative of this, I should get back to here. So derivative of 2x squared is 4x. Derivative of 2x is 2. All right, so this is the antiderivative, and now I'm going to plug in my top bound first. I'm going to plug in 5. I'm going to do this all in red. All right, so everything in these red parentheses is plugging in 5. Then I'm going to subtract. I'll do this in green when I plug in 2. A lot of 2's in that one. And generally what I like to do is simplify this whole parentheses into one number, this whole parentheses into one number, and then just subtract the final answer. So this is going to be 50 minus 10, which is 40. This is going to be 8 minus 4, which is 4. And now I got these two separate ones. I subtract and I get 36. Right. So my final answer here, the exact area is 36. All right. Another one. Again, same idea. We're using the fundamental theorem of calculus part 2. So the first thing I'm going to do is take the antiderivative of this. So I'm going to start off with 6x. I'm going to add 1 to the exponent. So it's going to be 6x cubed over 3 plus 2x to the first. It's going to be 2x squared over 2. And evaluate it from 0 to 2. All right, again, before I evaluate, I want to simplify. So 6 divided by 3 is 2. 2's cancel out. And again, one of the most common mistakes is just plugging in the wrong thing first. Plugging in 2 first. All right, so that's when I plug in my first value. Then I subtract when I plug in my second value. I like to kind of simplify them separately. So this is 2 cubed, 2, 4, 8, times another 2 is 16. And this one's pretty nice because I just get 0 when I plug in 0, so I get 20 as my final answer. And one more using this thing just to make it a little bit more complicated. We don't just have the reversed power rule right away. What I have to do is remember that the square root, and you'll just, at this point in the semester, you should be really used to this. Whenever you see a square root, just basically think about it as x to the 1/2. And now I want to take the antiderivative of this, so I'm going to take x to the 1/2. I add 1 to the exponent first, and then divide by the new exponent. Dividing by 3/2 is the same thing as multiplying by 2/3. All right, that's just the simplifying step. Oh, and I've forgotten each of these things. We're evaluating this from 4 to 9. And once I start to go plug things in, fractional exponents don't really make sense in my head, so I'll rewrite it as a square root again. So it's going to be 2/3. The 1/2, or that 2 on the bottom, turns it back into a square root. And now there's x cubed, evaluated from 4 to 9. And actually, one thing you can do to make it a little bit simpler, I have x cubed and then the square root. I could actually put this cube after the square root, and that'll just make the numbers a little bit smaller. All right, so let's go ahead and do this now. So I plug in 9 first. 2/3 times the square root of 9 cubed minus 2/3 times the square root of 4 cubed. You know how to do those square roots. Do the cubes. Exponents are next. Let's see, 27 divided by 3 is 9. 9 times 2 is 18. This is 16 over 3. All right, let's just leave it there. You can combine them or get a decimal answer. 18 minus 16 over 3, get a common denominator. So I'm not going to do it in the video. Save 30 seconds. All right, our next skill is finding the antiderivative of a function using substitution. All right, so we're just finding the antiderivative here. I don't want you to take all that extra time to plug in values. So we just need to figure out how do we take the antiderivative of this expression. All right, and again, I've said this a lot when we learn this. All right, just make sure you write out all the steps, because if you don't write out all the steps, you're definitely going to make a small mistake at the end, either with negatives or kind of what constants are left over. So generally, the thing we're going to pick for a substitution is something that's inside of something else. So right now there's this parentheses here. So my first guess would be to make u 3x squared minus 4. Sometimes you pick a u and it just doesn't work out, all right, but it is, a trial and error. But a lot of times if you look inside parentheses, that's going to be your u value. All right, now I take derivatives of this expression. So u, its derivative is du, and this is 6x dx, because the 4 goes away. I want to solve for dx. I'm going to replace that dx up there, so I just divide the 6x to the other side. All right, so now I can rewrite my expression. This is the same as the integral of 6x over this whole thing I called u, so this is now u to the 4th power. and dx is going to get replaced by du over 6x. And in this problem, we do get a little lucky that this just completely cancels out, and this is the same as 1 over u to the 4th du. So now I just have to remember, how do I take the derivative of 1 over u to the 4th? I remember that that is u to the negative 4. And then I do the reverse power rule. So I add 1 to the exponent. Negative 4 plus 1 is negative 3. Divide by the new exponent. And remember, here we're just doing our basic antiderivatives. We don't know if there's a constant, so we have to add that plus c. And I will write this as 1 over negative 3 u cubed, because I like positive exponents instead of negative exponents. And by me saying I like, it also means the AP exam is going to rather have it as a positive exponent. And my very last step is remembering u is actually just the placeholder for something. So my final answer is 1 over negative 3 times 3x squared minus 4 to the positive 3 plus c. All right, so really make sure you write out all these steps. I especially like the stuff in red to figure out what your fraction is here that you're replacing. And make sure you're comfortable with doing the reverse power rule once you do the substitution. And then make sure you undo the substitution at the end as well. All right, so here's another problem. If you just look at it right away, you're like, oh, I can't take this derivative using our normal method, so we have to do substitution. So here, what is our u going to be? It's something that's inside of something else. Well, here the only thing it could be inside of is this cube root. So my u is going to be 2x minus 5, which means du is just 2 dx. And then divide by 2, du over 2 is dx. All right, so now my integral becomes 16 cube root of u times du over 2. All right, and here's where it's important to write out all this red stuff, because here these numbers don't completely cancel out, but I do get a little bit of simplifying, and now it's just 8 cube root of u du. And now I just need to remember how to take the antiderivative of this. So the first thing we do is whenever I have a constant multiple inside my integral, I can just bring it out to the front. So it's going to be 8 integral or antiderivative of u, or the cube root of u is the same as u to the 1/3 du. So now that I have it written as just a power inside this integral, I can do the reverse power rule. 1/3 plus 1 is 4/3, and I divide by the new power 4/3. Now it's just simplifying. Dividing by 4/3 is the same as multiplying by 3 over 4. 8 divided by 4 is 2, so it turns into 6 u to the 4/3. And we can write that as 6 2x minus 5 to the 4/3. I'd be happy with this, but again, a lot of times you want to convert this back to a root again, so you might see it like this as well. All right, something like that. All right, the 4 can be in the inside or the outside, but this is probably how you would see it as a multiple choice question, but this would also be acceptable. All right, another one, very similar. All right, what is your u going to be? That's a question you should be able to answer for yourself. Use inside the parentheses. U is 2 minus 3x squared. Du is negative 6x dx. So du over negative 6x is dx. Right, again, write out those steps to make sure you get all the numbers correct. And now my integral. Right, 2 minus 3x squared is u, so now it's u to the 4th. Dx is du over negative 6x. So one way I know I picked the right u is the x's do cancel. So that x and that x cancel. These numbers don't fully cancel, so we're going to do the same thing we did on the last example. I can rewrite this as what? Negative 5 over 3 u to the 4th du. But whenever I have a constant multiple, I can just write it in the front of the integral. All right, that's just going to hang out when I do my antiderivative. So my antiderivative of u to the 4th is u to the 5th over 5. Here the 5s are going to cancel out, so that's negative 1/3 u to the 5th. And I replace u, it's negative 1/3, 2 minus 3x squared raised to the 5th. Plus c. right, so that's our last one for doing substitution. All right, just look at the parentheses. U is going to be the thing that's in the parentheses or in the root. All right, just make sure you write out all the steps. The most times I see students making mistakes is they're just not writing out the steps that they need to. Oh, there's one more substitution one. All right, same thing. This one's very similar to the last problem. Again, we just have to be careful with all of our simplifying. So let's do this one really quick. Du is going to be 6x dx. Somehow we got 6x for a lot of these answers. That's not always the case, obviously. All right, 3x squared minus 1 is u, so now this is u cubed, and dx is du over 6x. Again, you know you pretty much did it right if the x's cancel out, because now I just have a simpler expression with u. This is 1/2 integral of u cubed du. The 1/2 is going to stay. U cubed is going to turn into u to the 4th over 4. When I combine these, I get 1/8 u to the 4th. And replacing u, I get 3x squared minus 1 to the 4th plus c. All right, so that's a review of everything. I know I did the last example really quickly, but you saw 3 substitutions problems before that, and that one's really simple to question, or similar to question 3. All right, so just keep looking through that practice test. Make sure you know all those skills. All right, finding areas using geometry, Riemann sums, tables or expressions, and then how to do these exact things using the fundamental theorem. All right, so make sure you look over all that, and then let me know if you have any questions before we get to the test.